Okay, here are the rest of the notes. Now we're going to start looking at some cubic functions, okay? So cubic functions, because the degree is 3, we're expecting to find 3 roots, which might look like x-intercepts. And in this first one, they are x-intercepts. You can physically see them. And it looks like we have one at 0, 5, and -2. I think that's what they asked me to do here on number 7. Now, just because it looks like they are at 0, -2, and 5 doesn't necessarily mean they are, because in fact they could be in-betweeners that are hard to tell. So when they say use the equation to make sure that you're correct, they actually want you to plug in 0 into the equation, and I would get 0 to the third minus 3 times 0 squared minus 10 times 0. Is that a root? Does that equal 0? And the answer is yes. If you try -2, you would have -2 to the third, which is -8, minus 3 times -2 squared, which is -12, excuse me, minus 10 times -2, which is plus 20. That does equal 0, so it looks like we are doing things correctly. And then for 5, it would be 5 to the third minus 3 times 5 squared minus 10 times 5. 125 minus, what's that, 75 minus 50. Also a root. Okay, so after that, they're asking us to write it in factored form. So now that we know the roots, you can write x minus the root to get factored form. So it would be x minus 0, x minus -2, which would be a plus 2, and an x minus 5. But we don't usually write things like this with the x minus 0. So it would just be x plus 2, and x minus 5. They actually want you to multiply to show that it's correct. Anytime I multiply, I always do the 2 pieces first. I'm pretty fast at multiplying them. So it's x times, what's that, x squared minus 3x minus 10. Distribute the x at the end, and you get x to the third minus 3x squared minus 10x, which is what we were looking at. So they ask you, are the results consistent with the fundamental theorem? Yeah. The degree is 3. We have 3 roots. And actually, they were real roots, and they showed up as x-intercepts. Moving on. This one, the degree is 3, so we're looking for 3, but it looks like there are only 2 x-intercepts. So it looks like maybe you're at -4 and 1, but because this is a bounce, the -4 is what we would call a double root or multiplicity 2. That can show up in factored form by x minus the root. So x minus -4 would be an x plus 4, but since it is a double root, we would square it and then an x minus 1. So if you have a graph, what we're finding is you used to not have the skill set to factor something that's to the third power, but now if you have a graph, you can, as long as you can see where the x-intercepts are. They want to verify that it's correct. Don't forget, that's x plus 4 times x plus 4. So it's x squared plus 8x plus 16. Take that times x minus 1, and this problem's a little bit more tricky. X to the third minus x squared plus 8x squared minus 8x plus 16x minus 16 after I distribute all the pieces. Combine like terms, and we do get what we started with, x to the third plus 7x squared plus 8x minus 16. So I just jumped down and did number 11, even though you couldn't quite see the question there. Okay, is that consistent with the fundamental theorem of algebra? Yes, the degree was 3. There were 3 roots. Even though there was only 2 unique roots, the one was a double root. What was the double root? -4 had multiplicity 2, so that one does count twice, and it does follow that fundamental theorem of algebra. So you can see how that is helpful when you're looking for solutions. Okay, this is the last one we're going to talk about. And this is the mother function x to the third. The degree is 3, so there should be 3 roots. But see, do you see this? I call it the hesitation. I used to tell kids when I would teach them in class, have you ever seen the movie Stranger Things or the TV show? When they're thinking about going into the other side, they like get there to the edge and then they like hesitate and then they pass through. Well, that's what a triple root looks like. It's like a hesitation. The rate of change actually slows before it passes through. Because like, should I go through? Okay, I'll go through. And all odd multiplicities do look that way with a hesitation. If it's an x to the fifth, it hesitates even steeper before it goes in. But if it looks like it levels off before it passes through, it's an odd root. And usually it's going to be a 3. So it is a triple root, multiplicity 3. That is why it is consistent. So then they give us one like this. And this time they did not write it in standard form, which I find that interesting because they want us to do it, I guess. So I could tell you what it is in standard form. I could go ahead and double distribute this if you want to know, because now I kind of do. X to the third plus 3x squared plus 4x plus 12. Okay, so this is a standard equation. The degree is 3. So you should be looking for 3 roots, but all I see is 1. And that shows up right here in that first factor. Now, the second 2 that don't show up, because you can't see them, is because they are imaginary roots. How can I find them? How can I find them? Well, since this one is -3, by changing the sign of that factor, this guy could set equal to 0 to find the last 2. X squared plus 4, if it was to equal 0 and I subtract 4 from both sides, x squared is -4, square root both sides. My last 2 are plus or minus 2i. Okay, they want me to verify that it's true by plugging it in on question 15. -3 is easy to check. When I plug in -3 here, -3 plus 3 is 0. 0 times -3 squared plus 4. Well, 0 times anything is 0, so that does work. 2i is trickier. I would have 2i plus 3 for the first parenthesis. And here, when I have 2i squared plus 4, 2i squared is 4i squared, which is -4. So -4 plus 4 is the 0 times 2i plus 3. Anything times 0 is 0, so the 2i works. -2i I could plug in as well. Plug it in here. -2i plus 3 times -2i squared plus 4. -2i plus 3. That will be 4i squared again, plus 4, which is -4, plus 4, which is 0. So it also is going to equal 0. So this little wiggle away from the x-intercept kind of lets you know that there's going to be imaginary roots. This is consistent with the fundamental theorem algebra. Degree was 3. Ooh, look at that big space there. The degree was 3, and there were 3 roots. There was only 1 real, and there was 2 imaginary. Imaginaries always come in pairs, so that makes sense. How, if you have the factors, can you explain how to find the factored form? If you have the roots, the factored form is just x minus parenthesis, the roots. Okay, the parentheses will be important in case of something like a 2 plus 3i or something like that. And how can you find the roots? If you know the factors, you can set them equal to 0. You could set each factor equal to 0. Or you could change the sign of the root if it's a simple one like this. Okay, that's it for the notes. It was kind of a lot today, I'm not going to lie. I think you'll take the worksheet tomorrow. That was not too hard. I'm going to go ahead and post that shortly too, so some people can work ahead if they want.